All right, so in this video, you're going to see angular momentum. Angular momentum is pretty cool. You can analyze all kinds of things. So let's take a look. So here we have an object rotating, and then all of a sudden its angular speed increases. We'll be able to explain this with angular momentum. Okay. Here we can see this guy does a double backflip. Okay. He goes up, not rotating very fast, and then he increases his angular speed. Again, angular momentum lets us explain that.
Please start applying your net's torque.
So here you'll hear her say some terms that you'll get used to.
Watch
You should already know.
acceleration. Okay, let's let go of the torque. 1, 2, 3. Decrease your rotational inertia. Come on, you can do it. All right. 1, 2, 3. Increase your rotational inertia. Increase your rotational inertia. You can do it.
So you guys have heard some of those terms: net torque, increasing rotational inertia, decreasing, but maybe you hadn't seen all that effect. So now we'll be able to see what effect that has.
Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
All right, now you can become a champion of AP Physics by what we're going to learn about. So, as we can see, our figure skater definitely has a lot of stuff to do with angular momentum. So let's take a look. Well, remember, linear momentum and angular things are very similar. So linear momentum is just m times v. So angular momentum is the same part, but instead of m with angular, we do I, moment of inertia. Instead of linear velocity, we do angular velocity, which is omega. Then remember, this is our impulse equation for linear momentum, so that also works for angular momentum as well. Let's take a look at this as a point particle, because there's actually some interesting things. So L equals I omega. And then remember that I, for a point particle, is how that mass is distributed and how far it is from the axis of rotation, so mr squared. Then omega, well, if we're trying to do all linear terms here, remember, omega times r equals v, so omega equals v over r. So then this cancels out here. So angular momentum, I'm going to write it just a little bit different, is just mv times r. So here you're left with something really nice, that angular momentum is mv, which is linear momentum, times r. And we're going to put this as r perpendicular here to show you in just a second. So angular momentum is also linear momentum times r perpendicular for a point particle. And we'll show you why this is important later on. So let's look here at some point masses and why this matters. So let's say I have a rod, okay, and that rod has a pin in it. And I'm going to throw a ball, this velocity, directly at that pin. And then let's try a ball here. All balls have the same mass, this velocity here. And here we go. And this velocity here. Okay, so the interesting thing that we just talked about, L for a angular momentum for a point particle, which all these masses would be point particles, is linear momentum times r. But you may ask, how can something that's not rotating, right, all of these balls are not rotating, so how can they have angular quantities? Well, because we're going to see after a collision, in some of these cases, this rod is going to rotate and you're going to have an angular velocity. So remember, we talked about conservation of linear momentum. So we'll see here in just a second, you'll have conservation of angular momentum. So if I have angular momentum after a collision, I must have had angular momentum before the collision. So let's take a look at this. Okay? So on this one, if I have this object and I throw it right at the axis of rotation, remember, if we think about forces, right here I would have force of rod on ball. And then I would have Newton's third law, because we're going to look at things from a system perspective. I would also have the ball on the rod. So neither of those forces exerts a torque. So for that one, this rod won't rotate. So if that's the case, then this had zero angular momentum. So you could see it had linear momentum, but again, did it have a perpendicular distance? Okay, and R perpendicular can be the distance, and it has to be perpendicular from our axis of rotation to the velocity line. Because what about this one? If I hit right here again, yes, this would have a torque, so this thing is going to rotate. So this must have had an angular momentum. And the reason it does is because if you think about it right here, there is that R perpendicular. So if your linear object has a perpendicular distance from the axis of rotation, then you have angular momentum, which we see here. Which one of these has the most angular momentum? That would be this one. If the rod hits here, okay, because the force we're assuming is all the same, but this last one, it has a greater perpendicular distance, so it is going to cause a greater rotation. So that's how a point mass, an object moving linearly, can have angular momentum. So now let's take a look at conservation of angular momentum. Now this still comes to play for everything linearly. Okay? So F net times T is change in momentum. And then remember, this could then be, you could do the same thing here. You could do all of these concepts that you could put in. So be prepared to do the exact same thing with rotation. So remember that when is linear momentum conserved? That is when F net on a system equals 0. So when our F net on our system equals 0, then our change in linear momentum is 0. So then we said momentum initial equals momentum final. And that was derived from momentum initial plus change in momentum equals momentum final. This is the main one we looked at. But when F net of the system equals 0, then we could see that whatever I start with, I have to end with. So let's do all the same. So instead of instead of F net, I have torque net times time. Instead of linear momentum, I have angular momentum. Sorry, that should be an L. So then this could be LF minus LI. This could be M, which is I times omega change in omega. And then you can just keep going on and on and on, all the exact same equations for one we could do for the other. So for this one, if F net on the system equals 0, then when torque net on the system equals 0, your change in angular momentum equals 0. So then Li plus change in angular momentum equals LF. So if this is true, Li equals LF. And so that's what we'll be looking at for conservation of angular momentum. So it's really, really important that here F net and torque net have to equal 0. So your free body diagram on your system is insanely important, because that's how you're going to be able to answer these. Most likely they're also going to ask conceptual questions, so that's where you need to be able to understand what's going on. So let's look at this example. What happens to an ice skater's kinetic energy rotational, and how did this change? Well, first, let's look at forces. So the forces, right, we still know you got gravity down, normal force up. Okay? Those are equal, so the net force is 0. When you pull your arms inside, there are no external forces. That's just your muscles pulling on each other, so there are no external forces. So your force net external equals 0. Also, these forces go through the axis of rotation, right? The axis of rotation is up and down, how you're spinning around. If there was like a rod all the way through, it's spinning around that. So I know my F net on my system equals 0, and I know the torque net on my system also equals 0. So that means that linear momentum is conserved and angular momentum is conserved. So momentum initial equals momentum final, and Li equals Lf. So now we want to get to rotational kinetic energy. So kinetic energy rotational is 1/2 I omega squared. So I'm going to have to talk about those. And the best part about this is that's what it talks about. So we have, let's call I initial times omega initial equals I final times omega final. And so we want to see what changes happened. Right? So we can see that we'll say this side, hey, that's what we originally started with, and this side is constant. Okay? So if this side is constant, then let's think about what changes we had happen. So here, IF, as you can see, they say it got small. So if this goes down, what should happen to omega final? Well, if it has to balance out on the left side, then this will have to get larger. And so that's why you can see as that person pulls their arms in, they get a smaller rotational inertia that gets a larger omega final or angular speed. If numbers help you, okay, remember the left side is constant, so we're not going to worry about that. So what happens if I got 1/2 of my omega initial, or sorry, moment of inertia initial? What would have to happen to my omega final? Right? And let's do this I. So I initial, omega initial. So on this side, I have this extra 1/2. Remember, this side can't change. So what would I have to do here to omega final? Well, what if I said omega final then is 2, remember I'm just plugging in what these things equal, omega initial. These two canceled out, so I have I initial, omega initial equals I initial, omega initial. So that means omega final had to be 2 times omega initial. So it had to double if you got half of the moment of inertia. Now, let's go back and see how we could solve that whole problem with rotational kinetic energy. Well, here, this is 1/2 I, and let's just say, okay, I goes down, okay? So that would mean kinetic energy rotational would go down. But be careful, this is a common thing that people do. They look at one variable and they say, oh, that went down, so this had to go down. But that is not correct, right? You have to analyze all variables. So we know I goes down, but then we also know that omega final went up. So which one affected it more? And so that's what we're going to have to look at here. So here that omega final had to go up. So which one affects it more? Well, that's kind of hard to tell. So, well, we just looked here that they are actually inverses of each other. So one went down by half, the other doubled. But then in the equation, which one affects things more? Moment of inertia or omega? Well, since omega is squared, it has a greater effect. So no matter what happens to I, you can really look for kinetic energy rotational. You can look at omega only. That's kind of nice. So K rotational must have increased in that problem. Let's take another look here. Right. So I have a small mass attached to a string. It goes in. Let's see how to do this. I'm going to change this to 0.40 instead of 0.48. So let's talk about how do you do all momentum problems. Free body diagram makes up everything. All right, so what is the net force? Right? Well, Fn and Fg will cancel, but Ft doesn't cancel, so this is not equal to 0. So the change in momentum does not equal 0, so the momentum here is going to change. Mass stays constant, right? So velocity in this scenario will have to go up or down. So looking for a velocity there to change. What else? So now torques. Well, if we think about Fn and Fg, those both may create a torque, but they cancel each other out, so that doesn't change any rotation. Here, Ft, that force goes through the axis of rotation, so that force does not create a torque. So here, linear momentum is not conserved, but angular momentum is conserved. That's not angular, that's not what I wanted. Angular momentum is conserved. So Li must equal Lf. So we have I initial, omega initial must equal I final, omega final. So then here we could go and we could balance everything out, try and solve this. So this way you could look at it and you could say, okay, well, I is mr squared. If I want to do velocities, this would then be v over r, so that cancels. Equals, and I should put final, initial and initial. So this is mv initial, r initial. And this then is mr final squared, v over r final squared. And so this equals mv final, r final. So you could then just plug in whatever you needed. Now remember, there's another method from this line going down. If you want to just do linear momentum, you could have said linear momentum initial times r initial equals linear momentum final times r final. And then you would end up with mv initial r initial equals mv final r final. So you end up with the same thing either way. So on this one, let's do a quick thought about this one and see what happens. So the radius started at 0.8 and then it went to 0.4. So remember, angular momentum is conserved, so let's just think about what happened. Okay? So this has to be constant. When my radius goes down, that is decreasing my moment of inertia is going down, so this thing must get faster. Also, if you went down to this, you could see I'm getting half the radius. Oops, no, wrong side. Okay. I'm going to get half the radius. Mass can't change, so I have to get twice the velocity for this to cancel out. So this thing should end up at 4.8 on that one. A couple more examples here. So a person stands to the side. They're rotating. If he raises his arm, what's happening to the speed of rotation? So let's, instead of doing that, because it's kind of messed up, what's happening to the speed of rotation? Well, again, the force is there. There's nothing new being added. That's an internal force by you lifting your arms. So the change in angular momentum is 0 because the F net equals 0 and torque net equals 0. Also, you could say change in angular momentum is 0. So linear momentum. So that's going to be constant. And that makes sense because this guy, does he even have any linear motion? No, he's only rotating. So he's not going to start moving linearly. He started at rest, so he's going to end up staying at rest linearly. He does, however, have a rotation. So angular momentum is conserved. Again, you could just look at this and say, since angular momentum is constant, when he raises his arms, what happens to his eye? So, what do you think? Does it increase, decrease, or stay the same? it should increase because there's more mass farther from the axis of rotation. Axis of rotation is like there's a line going down through him, and now he has some mass that is farther from that line. So if I goes up, omega must go down, and so that's what you could see here. It said his speed decreased. I'm more apt to think that's the type of question they're going to ask us, and we have to explain. And you would have to go through, well, how do I know that this is constant? Because the torque net is 0. There's no forces doing torques, so the angular momentum is constant. Since it's constant, I know his moment of inertia increases because he's getting more mass farther out, so then he will have to rotate slower, is how you want to walk through that one. All right, now they do collisions, and so they would ask us again on this one, what are the forces going on? Well, when this thing hits, I have force of rod on disc, and then Newton's third law to that, force of disc, and remember those are equal, disc on rod. So those two are equal, also they're through the axis of rotation, so nothing is creating a torque. So your torque net equals 0, so your change in angular momentum is 0, so whatever I start with, I have to end with for my angular momentum. So let's try and walk through what it would look like to be able to solve this. What's going to happen to the angular frequency? Okay. So to do this, well, we start with the only thing rotating to begin with, because this had a linear velocity, and that linear velocity is going right through the axis of rotation. So if I did angular velocity equals momentum times r, this r here is 0, so that doesn't do anything. So L of the disk is the only thing that has angular momentum. Afterwards, they stick together, so they have a system, and so I have a total. Again, how could I solve this? I could say moment of inertia of the disk times omega of the disk equals L total. Well, remember, you can do a system for your I, so I total times omega total. And so then you could be able to analyze that. You'd have to be given something for I of the disk, omega of the disk, and then I can be broken up into I of disk plus I of the rod. So you sometimes have to look at your I as a system, is how that one could be set up. Here's an old multiple choice problem. Let's take a look at this one. So the diagram above shows a child mass m on a platform of 5m that's rotating counterclockwise. There's no friction between this. So which of the following describes what the child could do to increase angular momentum? Well, let's talk about forces. Okay, so here's the center of the circle. If I did that, and let's say the child's right here. So here's that child. So let's look first if they walk towards the center. Well, the first one, I know I have gravity and normal force. Neither of those, well, those would cancel each other out. There is a R, and those are perpendicular, but they would cancel each other out, so those don't create a torque. Then what else do we have going on? Well, I have what's pushing him forward. So that's the ground, so force of friction, and that is the, we'll call that the platform on the child. But then Newton's third law, if we're looking at that, remember child platform system, I would also have force of friction of child on platform. So those two, they're also going through the axis of rotation, so those don't create a torque, and they would cancel out. And then the last one, well, if there's a force on the platform going this way and the platform doesn't move, well, this thing probably has like a stake in it. You saw some merry-go-rounds. There's probably like a pole that this thing is spinning around. So then if the merry-go-round doesn't move to the right because there's a force on it, then there had to be the force of this pole on the platform. So on this one, my F net does not equal 0, because what you're going to see is this student will probably actually speed up, okay? But the torque net does equal 0, because none of these forces that I've drawn here actually do a torque. So walking towards the center, the person may speed up or slow down, but the angular momentum is conserved because torque net equals 0. Walking away from the center. Well, that's going to be all these forces, except a couple of the directions are going to be flipped. Okay? This force here on the pole would be to the right. But again, your torque net equals 0. What about if the person was standing and it says walking one direction here? So what are the forces? So here, if I go this direction, then I have the force of friction of the platform on the child that way. And then Newton's third law, I also have the force of friction of the child on the platform going that direction. Hey, these are creating a torque. So if I had force of friction to the left, that's going to make the disc or the platform speed up. And then this would make the child slow down for angularly. But again, these torques cancel out, so torque net equals 0. So change in angular momentum has to be 0. Okay, so this also wouldn't do that. So none of these would actually change the angular momentum. If you really focus on forces, that's going to be the huge aspect that's going to be able to help you there.